everybody, let's do a recap of the big takeaways from today's lesson. So we are trying to focus on how could we find a brute force solution to the 8 queens puzzle. And all brute force solutions have the same type of structure. We're going to loop over every single possible solution and then check it to see if it is actually a solution. So my first piece of advice is don't try and think about the code in the abstract. You want to think in terms of specific examples. So ask yourself, what is a possible solution? What does that even look like? What am I going to give as an input to the check method? So for this particular problem, a possible solution is just 8 queens on a board. As soon as you've put 8 queens on the chessboard, then you can check to see are they threatening each other, and that's a possible solution. So our question is, how can we systematically generate all the ways of placing 8 queens on a chessboard? Several people were trying to do this at random. They had a loop and they were generating random coordinates. That's not brute force search, that's random search, which is also sometimes helpful. But right now we're trying to focus on how could you systematically be sure that you cover all the possibilities. It's very tempting when you have a two-dimensional data structure to think, well, I'm just going to loop over it. Because so many of the things we do involve checking each of the locations. And this double for loop is the typical way of checking each of the locations for something. But it's important to focus on what are you trying to do, not just what are things that you frequently do. So this makes sense if what you're trying to do is visit every single location. But here we're trying to place 8 queens on a board. So it's like not really clear what you do in the middle here. Like what are you doing at every single location that's going to eventually lead to there being 8 queens on a board? It's like these two things don't really feel like they have much to do with each other. So that's a sign that this is not the right approach to take. Instead, focus on what are all of the parts that constitute a possible solution. So for us, we have to make 8 choices. We have to choose for each queen where is its location. So each choice that we make, you can loop over all the options for that choice with a loop. So if I'm making 8 queens, if I'm placing 8 queens, maybe it makes sense to have 8 loops. And each loop is going to visit all of the possible options for where to place that particular queen. So this is one version of what that could look like. Up at the top, I'm generating a list of all possible locations and their location objects. So they've got a row and a column. And then I'm saying queen 1 is going to take on each of those possible values. So there's 64 possible locations. So queen 1 is going to visit each of the 64 possible locations. And then for each of those, we're going to try queen 2 at each of the possible 64 locations. And for each of those, we're going to place queen 3 at each of the possible 64 locations. So this makes sense as a way of systematically generating all the possible configurations of queens. The problem is the search space is absolutely gigantic. It's 64 to the 8th power, which is in the trillions of things to check. So one of the big takeaways from today is the idea of narrowing the search space. So a lot of the configurations that this is going to generate are ones that we wouldn't even want to check. So imagine, what is the first thing that this is likely to check? So imagine that our list of locations, the first location in the list is the upper left-hand corner. So as we go through the for loops, we're going to say put queen 1 in the upper left-hand corner, and then put queen 2 in the upper left-hand corner, and then put 3 in the upper left-hand corner. So all 8 queens, the first time through the loop, are going to get assigned to the upper left-hand corner, which means that we're going to check a solution where all 8 queens are in the same spot. So it would be nice not to generate that possibility and then check it to see if it's actually a solution. It would be nice never to generate that possibility at all. And that's what narrowing the search space is about. It's about cutting out certain options that you know in advance aren't going to be solutions, and that reduces the total number of things that you have to check. So what if we agree that we're going to place 8 queens, but 1 queen goes in each column? So we're not going to choose the columns. Like queen 0 starts at column 0, and queen 1 starts at column 1, and queen 2 starts at column 2. So what are we choosing? All we're choosing for each queen is which row that they're going to be in. So you can still have 8 loops because you're still making a choice for every single queen. But now the choice is, for the queen in column 0, which row is she going to be in? 0 through 7. And then for the queen in column 1, what row is she going to be in? 0 through 7. So this still covers all the possible configurations that might have a solution, but there's way fewer of them. Now there's only 8 options per loop, and that's 8 to the 8th power, which is only 16 million things. So that's why narrowing your search space is so powerful. On the order of hundreds of trillions of things might not be feasible to check, but if you're only checking 16 million things, you might be able to run that on your laptop. So here's like a specific concrete example of what this might look like. I could just have a one-dimensional array where it says column here. This is just the index numbers. So these values in blue up here, these are the actual numbers inside the array. So at index 0, that represents the queen at column 0, and she's in row 6. And the queen in column 1 is in row 2, and the queen in column 2 is in row 3, and so on. Okay, so then the second big piece of learning here is the idea that the data structure that you choose to represent your information can have huge impacts on how difficult it is to find a solution, on what your code looks like when you do, on how quickly your code runs. So I think it's natural when working or when thinking about something that feels two-dimensional, you want to make it into a two-dimensional structure. So here I'm making a two-dimensional board, and I'm putting integers that represent queens in all the locations where I calculated that there should be queens. So I'd said that a great way to start writing code if you're unsure is to start by taking a concrete example and think, as a human being, how would I answer the question that I'm trying to answer? So we're trying to answer the question, do any queens threaten each other? So there aren't 8 queens here, but there's some. So you can look as a human being. Do you think any of these queens are threatening each other? And then pay attention to what you as a human are actually doing. So I'm not sure what you're doing, but here's what my eyeball is doing. I'm scanning until I find a queen. So I'm like, okay, here's a queen. And then my eyeball is looking in each of the possible directions that the queen could move in to say, do I see another queen? So my eye looked here, and then I said, oh, queen there. Yes, there's a collision. Let's pretend this queen wasn't here. What could we do? So I would scan here, and I'd say, okay, I found a queen. No collision there, no collision there. Looks like, oh, I found a collision here. So that's the idea. So how could you take that idea about what your eyeball is doing and make it into some code? So what I just said is, let's loop over all possible board locations to find queens. So for each row, let's loop over each column, and then we want to know, is there a queen there? So if board at row column equals queen, then what do we want to do? Then we want to check if that queen threatens anything. This might be a nice place for a helper method. So we can say, if has threat, and then I'm going to give it the row and the column where we found the queen. So if there's a threat on that row or column, we can return false because we know it's not a solution. Okay, so what does has threat look like? So all I need to do is look in each of the possible directions from this row and column. So I could say for all rows to the right, check if there's a queen. So if queen, return false. For all rows to the left, for all columns to the right, for all columns to the left. If there's a queen, return false. For all the rows above, for all the rows below. So in other words, I'm going to loop right, I'm going to loop down, I'm going to loop up, I'm going to loop along all 4 diagonals. And that's it. I'm just going to look in all the directions and see, do I see another queen? That's it. A different approach that we discussed was loop over every single row and then have a method where you tell it the row and it will count how many queens are in that row. And if the number of queens is ever 2 or more, then you know that they're threatening each other, so it's not a solution. So you'd have to do that for each row, each column, and each diagonal in both directions. So all of these will work. The problem is it's going to generate a fair amount of code, and it's going to be kind of slow to run. So the second big takeaway is you don't have to store this information in a 2D array. This is what it might look like in a 2D array. We've got zeros, and then there's queens. I'm assuming this is an integer. There are queens in certain locations. But most of these we don't care about. Like, all we really care about is the coordinates where each queen is. And we can save that idea in a different way. One way you could do it is with an array list of location objects. So each element in the array list contains a location object with the row and column where one of the queens is. A different way to do it would be like this. In this representation, I'm using the indexes themselves to represent the columns where a queen might be, and I'm using the values in the array to represent the rows where a queen might be. So in this particular example, I'm saying there's a queen at column 0, row 3. There's a queen at column 1, row 7. There's a queen at column 2, row 1. Okay, so how could we ask the same question using this data structure? If we want to know, are any queens threatening each other, we can really break that down into 3 questions. Are there any queens in the same row, or the same column, or the same diagonal? So as a human being, how would we answer this question? It seems like I want to look at these row numbers and say, are any of these row numbers the same? And I'm seeing a 3 here and a 3 there. So that would tell me, yes, we have 2 queens in the same row. You might notice that this follows the same pattern that we've been doing a lot recently, this idea where we're going to loop over every single pair of numbers in a list. And we need to loop over every pair of numbers in the list because we're checking for any 2 values, do they have the same row number? Because that's the only way we're going to systematically check to see if you ever have 2 values that are the same. So this is our kind of standard for I goes from 0 to 7, and then for j goes from I plus 1 to 7. So in other words, I loops over everything, and j loops over all the values in front of I, and that's guaranteed to visit all possible pairs, and then you can check each pair. Are they the same row? Okay, trick question. Are any queens in the same column? Well, it's actually impossible to have 2 queens in the same column with this way of representing the data, because the indices are column numbers. So what that would mean is I have 2 different numbers in the same index, but that's not possible in an array. So by choosing this particular way of saving the information, we get this one for free. It's like not even possible to generate that possibility. What about diagonals? If you imagine that these are 2 queens on the board that are along a diagonal, the definition of being along a diagonal is the difference in their columns is the same as the difference in their rows. You can think about it in terms of slope. If you have a slope of 1 or a slope of -1, that means that they lie along a diagonal from each other. So how could we check that? It's the exact same thing. As long as we're looping over all pairs of values, all you have to see is, for 2 possible values, compare their column numbers. So here the difference between 1 and 4 is 3. So we've got a delta C of 3. And let's compare the row numbers for those same points. The difference between 7 and 4 is also 3. So the delta row is also 3. So because they're the same difference in row and column, I know that they're along a diagonal from each other. So that's it. The big takeaways from today are that you can reduce the size of your search space by reducing the number of things that you're looping over. And a good way to do that is to start with whatever you can come up with, but then ask yourself, is this way of looping going to generate possibilities that would be silly to check? And if the answer is yes, try and figure out how you can adjust your loop boundaries so that you're not generating possibilities that you shouldn't be. Sometimes that might require that you think differently about what exactly you're choosing in order to make a possible solution for checking. The second big takeaway is choosing the right data structure can make the whole problem feel very, very different. And I hope that a big takeaway from class was like how different it felt to think about checking if queens are threatening each other on a 2D grid versus checking if queens are threatening each other using that one-dimensional array. It feels very different, and your code turns out very differently. So right now, the big takeaway is just remember that that's a thing. And we're going to look in more detail at this thing as we continue. But this is like a huge takeaway in computer science is selecting the right data structures can simplify your life enormously and make your code run more efficiently. Okay, good luck, everybody.